A doubly linked list is an advanced linear data structure widely used in computer science due to its powerful bidirectional traversal capabilities, efficient node manipulations, and dynamic memory allocation. It is an extension of the singly linked list, where each node contains three fields: a data field that stores the actual value, a pointer to the previous node, often called prev, and another pointer to the next node, called next. This dual pointer structure allows the list to be traversed from both the forward and backward directions, offering greater flexibility in inserting, deleting, and locating nodes compared to a singly linked list. The first node is referred to as the head, and the last node is referred to as the tail. The head's previous pointer is null because it has no predecessor, and the tail's next pointer is null because it has no successor. The operations that define and manipulate a doubly linked list include creation, insertion, searching, deletion, and displaying the elements of the list, each of which plays a crucial role in maintaining the structure. The creation of a doubly linked list begins with initializing the head pointer to null, signifying that the list is initially empty. When a new node is created, dynamic memory allocation is performed using mechanisms like malloc in C or the new operator in C+ and Java. The newly created node's data field is filled with the required value, while its next and prev pointers are set to null because it is not yet linked to any other node. If the list is empty, the head pointer is updated to point to this new node, and simultaneously this node becomes the tail of the list because it is the only node present. If more nodes are created sequentially, they are attached to the end of the list by updating the next pointer of the current tail to point to the new node and updating the prev pointer of the new node to point to the current tail. Finally, the tail pointer is updated to this newly added node. This process continues as long as new nodes are added, forming a chain of doubly linked nodes where each node maintains a bidirectional link with its neighbors. Insertion is one of the most important operations in a doubly linked list because it allows new nodes to be added at various positions such as at the beginning, at the end, or at a specific position in the middle of the list. The advantage of a doubly linked list is that insertion is more efficient and convenient due to the availability of both prev and next pointers. Insertion at the beginning involves creating a new node, setting its next pointer to the current head, and setting its prev pointer to null. Then the prev pointer of the current head is updated to point back to the new node, and the head pointer is moved to point to the new node, making it the first element of the list. If the list was initially empty, both head and tail pointers are assigned to the new node. Insertion at the end requires no traversal if the tail pointer is maintained. A new node is created. Its prev pointer is set to the current tail. Its next pointer is set to null, and then the next pointer of the tail is updated to point to the new node. Finally, the tail pointer is updated to this newly added node. This operation is efficient because the tail pointer provides direct access to the last node. Insertion at a specific position requires traversing the list to find the position where the new node is to be inserted. After locating the node at the chosen position, the new node's next pointer is set to point to the node currently at that location, and its prev pointer is set to the node before it. The node before the insertion point has its next pointer updated to the new node, and the node after the insertion point has its prev pointer updated to the new node. This insertion method ensures that both incoming and outgoing links are correctly preserved. If insertion occurs before the head or after the tail, the process merges into the special cases described earlier. Overall, Insertion in a doubly linked list benefits from direct access to predecessor and successor nodes, reducing pointer adjustments and ensuring efficient node management. Searching in a doubly linked list involves locating a node containing a specific value. The presence of two directional pointers provides flexibility to perform either forward search from the head or backward search from the tail. However, most implementations use forward traversal for simplicity. In a search operation, traversal begins from the head node, and each node's data value is compared to the target value. If a match is found, the index or pointer to the node is returned. Otherwise, traversal continues until the end of the list. Searching operates in O(n) time complexity because, in the worst case, all nodes must be examined. Although this is similar to the time complexity of a singly linked list, the doubly linked list provides the additional benefit of reverse traversal. If the target value is suspected to be near the end of the list, searching can begin from the tail and move backward using prev pointers. This bidirectional capability enhances search flexibility, especially in applications such as text editors, navigation through browser history, or playlist management where backward searching is frequently required. Searching also forms the basis for other operations such as deletion and insertion at arbitrary positions, as both operations require accurate location of nodes. Deletion in a doubly linked list is significantly more efficient than in a singly linked list, because each node has a prev pointer that provides direct access to the previous node, eliminating the need to traverse the list to locate it. The delete operation can occur at the beginning, at the end, or at a specific intermediate location. Deletion at the beginning involves updating the head pointer to the second node in the list and setting its prev pointer to null. Then the memory occupied by the original head node is delocated. If the list becomes empty after deletion, both head and tail pointers are set to null. Deletion at the end requires updating the tail pointer to the second last node. The next pointer of the new tail is set to null, and the memory of the old tail node is freed. The advantage of maintaining a tail pointer becomes evident here since direct access to the last node allows deletion without traversal. Deletion at a specific position involves finding the node to be deleted and adjusting its neighbor's pointers. The prev pointer of the node's next node is updated to point to its previous node, and the next pointer of the node's previous node is updated to point to its next node. This disconnects the node from the list, after which its memory is freed. Deletion operations must also handle edge cases such as deleting the only node in the list, deleting head or tail nodes, or handling invalid positions. The presence of bidirectional links simplifies pointer adjustment and ensures that deletion requires constant pointer updates regardless of node location, contributing to the efficiency of the doubly linked list in dynamic applications. Finally, the display operation in a doubly linked list allows users to view the contents of the list either in forward or reverse order. For forward display, traversal starts from the head and continues through each node by following the next pointers until the tail is reached. The data stored in each node is printed sequentially. For reverse display, traversal begins at the tail and proceeds backward by following the prev pointers until the head is reached. This dual direction display is a distinguishing feature of the doubly linked list, useful in applications such as undo-redo operations, train scheduling systems, and bidirectional navigation systems. Displaying the list validates the correctness of insertions and deletions, aids in debugging, and helps visualize the internal structure of the list. In conclusion, the operations of creation, Insertion, searching, deletion, and display collectively define the power and flexibility of a doubly linked list. Its bidirectional navigation, dynamic memory allocation, ease of insertion and deletion, and ability to display in both forward and backward directions make it one of the most efficient and versatile data structures. Doubly linked lists are widely used in memory management, system-level applications, tree implementations, navigation systems, and many software modules where dynamic manipulation of ordered data is essential. Their structure, although requiring more memory than singly linked lists, offers significant performance advantages and logical clarity, making them indispensable in efficient algorithm design.